Okay, good afternoon friends. We shall continue with our discussions on graph theory. Yesterday we had taken up a problem. The A matrix was given, please correct it, there is a minus sign here, I forgot to write that. 1 minus 1 0 0 0 0 0 minus 1 and so on. So, we shall work it out here. So, from A matrix, if you apply those transforms, what will be the possible next transform? I can change the sign of this, okay. I can change the sign of the second row. So, this will become 1 minus 1 0 0 0 0, then 0 1 0 1 0 1, okay. Then 0 0 1 1 0 0 1 0 minus 1 0 minus 1 0, okay. Then from here if I subtract this, this one was sign changed from the previous matrix. Then if I subtract row 1 from row 4, A2 row 1 is subtracted from row 4, you get 1 minus 1 0 0 0 0 0 1 0 1 0 1, then 0 0 1 1 0 0, then this minus this will give me 0, then 1, is that all right?
Yeah, 1,
then
1.
minus 1 minus 1, then 0 0 sorry minus 1 0, is that okay? 1 minus 1 0 minus 1 0, and then what do you do? This is having 1 here. So, if I subtract this from this, 2 minus 4, row 2 minus row 4, what do you get? A3 1 minus 1 0 0 0 0, then 0 1 0 1 0 1, then 0 0 1 1 0 0, then 2 minus 4 will give me 0 0, next, yes please. So, if I change the sign, I am subtracting 4 from 2, so that will become plus 1, then 1, then plus 1, then 1, is that okay? Now, if I subtract 4 from 3 or 3 from 4 and replace the 4th row, what do you get? A4 will be 1 minus 1 0 0 0 0 0 1 0 1 0 1, then 0 0 1 1 0 0, and then 0 0, I am subtracting this from this, so 0 0, then 1 1, is that all right? So, how is that echelon structure? So, 1 2 3, 4, 5, 6. Let us see the original graph. If this is a 5 node system including the reference, then what it was like. 1, so this is node 1, suppose this is node 1, element 1, this is node 1 and these are the elements, nodes 1, 2, 3, 4, fifth one is the reference. Alright. So, what will be the structure of the graph, the overall graph? Let us see, can you reconstruct the graph from the given A matrix we discussed last time? This was the original matrix. So, from A matrix, can you construct this? 1, minus 1, 0, 0, 0, 0. So, this is node 1, element 1 is going, okay. Then element 2 is coming in, alright. No other element is connected to node 1. Node 2 is connected to element 2, node 2 is connected to element 2. Mind you, this is also, this is not the original A matrix, this is actually an A matrix with some sign changes, otherwise both of them cannot be minus 2. Then node 2 is, okay, element 2 is connected between 1 and 2. Let us see, element 3 is between 3 and 4. So, if 3 is between, element 3 is between nodes 3 and 4, element 2, element 1 is between 1 and 4. So, this is 4, this is 2, okay. Then element 3 is between 3 and 4, okay. Element 4 is between 2 and 3.
The graph is going down, sir, on the TV.
Sorry. Okay. So, it was 1 and 4, 1 and 4, 1 and 2, 1 and 2, element 2, then 3 and 4, 3 and 4, then 2 and 3, 2 and 3, this is element 4, this is element 3, then element 5 is between 4 and 5. So, between 4 and 5, this is element 5, this is node 5, and between 2 and 5 is element number 6, 2 and 5 element number 6, this is node 5, okay. So, this was actually the structure. Okay, 1, 2, 2, 4, 3, 5. Now, these are the elements. For forming the tree, what are the elements that we have found here? 1, 2, 3 and 5. Let us see, 1, 2, 3 and 5. This is a possible tree. Is that okay? I could have had 1, 2, 4 and 6 also, or 1, 2, 3 and 6. That also could have been possible. But 1, 2, 3, 4 will not be possible here. 1, 2, 3, 4 will give you 1, 2, 3, 4 a closed loop without having any connection to this node. That would not have been a possible tree. It would have been a closed loop. Okay. So, 1, 2, 3, 4 will not be, it is not possible for us to get an echelon form with 1, 2, 3, 4 nodes by any manipulation. Is that clear? So, this is how we develop a possible tree. Now, once again let us come back to loop matrix, some relations we shall derive for the loop matrix. We have observed earlier that any matrix, loop matrix B multiplied by voltage V is equal to 0, where V is the vector of voltages, across the elements. So, if there are say 5 elements, then V1, V2, V3, V4, this will be the elements of the voltage vector, and this will be taken positive in the sense of the loop, taken positive in the sense of the loop direction. So, fundamental loop matrix we discussed last time. It will have two components. We can put the twigs on one side and the links on the other side. Okay. Twigs and links. If you put one link at a time, then this will be a unity matrix, is it not? If you put one link at a time and then call that as loop 1, loop 2, loops are numbered with the number of the link 1, link 2, link 3. Similarly, we call them loop 1, loop 2, loop 3. So, that will give me a unity matrix in this portion. Okay. Now, we also established this relation A into B transpose equal to a null vector. Is it not? Because the elements of A, if you remember what is an incidence matrix A? A will be consisting of the elements connected between nodes, and we are taking plus sign for the currents which are for the elements which are going out from the node, and entering the node will be given a minus sign. All right. So, you will find A into I is equal to 0. Will that be all right? You consider from a node, suppose these are the directions of the currents we have taken, I1, I2, I3. So, from A matrix, these are the elements 1, 2, 3, 4, 5, 6 and so on, and these are the nodes. So, element 1 will be connected between say node 1 and node 5 and so on. Element number 2, depending on the arrow direction, it may be minus 1 and plus 1 here. So, if I take the sum of these currents, I1 into plus 1, I2 into minus 1 and so on, suppose I2 is in this direction. So, at this node, first row multiplied by the current vector will give me 0, that is Kirchhoff's current law, is it not? I1 plus I2 plus I3, all the currents going out, if they are taken as positive, should be equal to 0. If there is a current coming in the opposite direction, it will be negative. So, and that is reflected in the A matrix. So, basically A into I is equal to 0 is our well known Kirchhoff's current law. Okay. Now, we have also discussed about this product A into B transpose equal to 0, all right. when you consider a particular node and a corresponding loop here, if you consider the elements of the loop matrix, there can be only two elements which can come into play in a particular loop. This element will not be included in this loop. So, in a particular loop where a node is included, there can be only two elements in that particular node which will be involved in the loop. And if the loop direction is like this is positive for A matrix elements, whereas this will be positive and this will be negative for the B matrix elements, is it not? So, if I take A into B, for example, if we consider this particular node, then nodes are having, there are many other elements connected to the node, but for a particular loop where there will be two non-zero entries, it will be this one and this one. This element does not come into the loop. So, even if there are ones or minus ones in the A matrix row, the corresponding elements here will be zeros. Only there are two elements involving these two non-zero elements here, and what will be their directions, what will be their signs? If this is plus 1 minus 1, this will be minus 1 minus 1 or plus 1 plus 1, so that product sum is 0, is it not? So, this also we established last time. By breaking up A, okay, into AT and AL and B into BT and unity matrix, we got AT partitioned AL multiplied by BT transpose U equal to 0, from where we finally wrote, see, AT into BT transpose plus AL is equal to 0. So, AT BT transpose equal to minus AL, which gave us BT transpose equal to minus AT inverse AL, AT inverse AL. Okay. This is what we got last time. I am just repeating some of the points that will be of some relevance now. Now, let us come to cut set matrix. What will be the relationship with this matrix cut set, relationship with B and A? QF cut set matrix, once again, if you have a graph, say maybe like this, I am just taking an example, I can have a cut set like this. Okay. So, these may be the directions of different elements. Now, depending on the choice of the tree, if you would have chosen the tree as this, say, suppose this is a tree, then this would have been a twig, a link, this would have been a link. Is that all right? So, if I want to have a cut set, I can, how do I cut this? Suppose I want to isolate this or I want to isolate this. So, this can be a cut set, is it not? I will cut one twig at a time. So, this will not be a possible cut set if I choose the tree like this, because two elements of the tree will be eliminated, in a cut set, in a fundamental cut set, I am talking about a fundamental cut set, there can be cut only in one of the tree elements. So, this is a possible cut set, fundamental cut set. Okay. Similarly, if I want to cut this, if I want to cut this twig, I should cut like this. I cannot cut like this, then two elements will be cut. Okay. So, whenever you are cutting one element of the tree at a time, okay, one element of the tree at a time, then what will you observe? Suppose we take twigs, the tree elements on this side and link elements on this side. If I call the first tree element, I can number them accordingly. First tree element, when it is being cut, this is cut set number 1. So, cut set 1, this will have 1 here, no other twig will be cut. So, I will get similarly for cut set 2, only element number 2 will be cut. So, it will give me what? A unity matrix in this side, in this side. So, it will be unity matrix and the remainder I will call it QL, okay, which will be containing all other elements involving the links. Okay. For example, in this cut set, what will be the elements here? They will be corresponding to this one, this one, this one and this one, is it not? If I consider this cut set, cutting this tree element, then this and this, these 4 dotted lines will be coming here. 4 dotted lines means 4 link elements. Okay. So, that will be giving me the submatrix QL. Okay. So, QT is U, and rank of this is an n by n, because how many twigs can you cut? If you are having n plus 1 nodes, then how many elements are there in a tree? N. And this is cut one at a time, so this will be n by n. So, the rank of QF is n. Is that all right? Number of nodes minus 1, that will be the rank of the fundamental cut set matrix. Okay. Now, you see Q, there is an interesting relationship between Q and B. Q into BT is equal to 0. Can you prove this? Q into BT, let us see what it means. When we are considering, say, this particular matrix or this particular tree, when we consider a cut set, I am cutting one twig at a time. Okay. There can be a loop, this loop. Okay. Let us consider this cut set. Okay. Now, with this tree element being cut, so this can be a possible loop, because we are taking the product of loop matrix transpose and Q matrix, all right. Now, what does it mean? Q, suppose the elements are Q matrix will be elements 1, 2, 3, 4, 5, 6, suppose it is a 7 element network, it is like this, all right, out of which I have chosen, suppose there are 4 nodes here, so C1, C2, C3, C4, barring the reference node there are 4 nodes left, all right. So, that is the order n. So, n by n, I have arranged the twigs, numbered them in such a way that the twigs are coming as element number 1, 2, 3, 4. Okay. So, this is the unity matrix and this is QL. okay, and B transpose will have 1, 2, 3, 4, 5, 6, 7 all the elements here. Okay. Now, let us see what will be the elements of this. Actually, this need not be arranged. I am just getting a general relationship Q into Bt, elements of this and elements of this, what will be the total products? What will be the product sum? Which one will be multiplied with which number on this side? In a cut set, one twig is being cut for the tree and there are other elements, but in the B matrix, what will be the values of this? There can be only two elements forming a loop, two elements which will be non-zero, which will be included in this, is it not? When I write the loop matrix, say this is loop 1, loop 2, loop 3, loop 4 and so on, there are so many loops depending on the number of links, okay. So that will be 1, 2, 3, loop 1, loop 2, loop 3, these are the fundamental loops, is it not, depending on the number of links. So in loop 1, if I put one link at a time, then that will form one closed loop. So you will be cutting only two elements of the loop which will be involved in the cut set. Other elements of the cut set, they are all links, but you are taking only one link at a time for a loop, is it not? So either these two will be non-zero, others are all 0. This will not come in this loop. This link, though it is cut by the cut set, though it is an element of the cut set, non-zero element of the cut set, plus 1 or minus 1, but in the loop it is not existing. So in the loop there are only two elements which are non-zero, is it not? And now you see the direction of the cut set. For example, suppose this is the direction of the tree, then the direction of the element of the tree, then the direction of the cut set, suppose this is the element of the link, then the cut set direction is taken as the direction of the twig. So the cut set direction is this. So for the cut set, this is plus, this is minus, next element is minus. These elements, whatever be the directions, they do not come into picture when I talk about the products of these, okay. So in the loop, this is plus 1, this is plus 1, whereas in the cut set this is plus 1, this is minus 1, alright. So what you get, one element is plus, one is minus, so far as the cut set matrix is concerned, and on this side both are plus 1. So if I take the product sum, it becomes 0. This is one possible combination. Had it been in the other direction, say both are plus 1, in the cut set elements both are plus 1, then in the loop one will be plus, the other one will be minus. So it will be 1 and minus 1 here. So if it is 1 1, it will be 1 minus 1 here, again end product will be 0. Do you get my point? So there are possible combinations 1 1, minus 1 1, 1 1, 1 minus 1, minus 1 minus 1, 1 minus 1, okay, or 1 minus 1, 1 1 and so on. This kind of combinations will be there, so that the final product sum is 0, okay. So Q into Bt is 0, alright. Now let us expand this. Q into Bt equal to 0. What is Q? Q is U partitioned QL, is it not? We got Q, we will consider only QF. This is a general relation for any Q, okay. If you take the fundamental cut set, then Q T and QL, Qt is unity, so I am writing unity into QL. And what was BT? What was BT? If you remember? Yes. How did you write BT? B transpose. B BT transpose and U. Was it like this? So BT transpose plus QL is equal to 0. This is equal to 0, is it not? Therefore, QL is how much? BT transpose. Okay. And how much did you get as minus BT transpose? Yes. 80 inverse AL. Okay. So QF is therefore U partitioned QL, and I can write this as U partitioned AT inverse AL. Is that okay?
Yes.
If I multiply by 80, if I multiply by 80 and take 80 inverse outside, inverse into 80 partitioned AL, which means nothing but A. 80 and AL combined together is A. So it is 80 inverse A. Is that okay? Now what is A into current vector I? Kirchhoff's current law, is it not? This is giving you the incidence matrix relationship with the elements and the nodes. So that gives me this relationship. So if I multiply by I, therefore QF into I is equal to 0. Is that all right? What does it physically mean?
Inside loop.
No, QF is a cut set matrix. So suppose I have a cut. So currents going here, 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 like this. Say there are many currents flowing through this. So currents flowing through only these elements will be non-zero. Other elements, there can be other elements here, but they don't come into picture. So far as this cut set is concerned, so this plus this algebraic sum of these currents will be 0. What does it mean? It means that if I have a cut set like this, suppose these are the two subnetworks connected by these lines.
So we are as if physically cutting the line.
Cutting, suppose cutting means you are imagining a scissor cut. So the total sum of currents is equal to 0. It is an extension of Kirchhoff's current law. Kirchhoff's current law talks about a node. Nodes, say the currents coming out of the node is equal to 0. Now we replace the node by a subnetwork. Currents coming out of a system, if I partition it, if I cut it, if I imagine this is one area, this is another area connected by many lines, then current coming out of a particular system is equal to 0. This is precisely we use in power systems. In two subnetworks, suppose two states, two areas are connected by different tie lines. So the total amount of current going out of the tie line will be equal to 0, is it not? It is an extended concept of Kirchhoff's current law. So QF into I equal to 0. Now, we would like to discuss something about formation of the Q matrix from A matrix. Before we go into that, we will be discussing a little bit about echelon form. Some transformations. Yes, please. Elementary operations or elementary transformations. Suppose you are having any matrix F, okay. Hello. Elements of the matrix F, is it not coming all right? These pens are drying up. So, suppose F is any matrix 1, -1, 0, 1 and so on. When we try to make those operations, changing the rows or interchanging or changing the sign, similar operations can be done by elementary transformation, we call it. You consider a unity matrix, say this is the identity matrix, okay. Suppose I interchange these two rows, row 2 and 3, then what do I get? 1, 0, 0, 0, 0, 1, 0, 1, 0. All right. This is an elementary matrix. That is, from the identity matrix, by interchanging the rows, we can always generate an elementary matrix. And elementary matrix, its inverse is also another elementary matrix. So, elementary matrix inverse is also another elementary matrix. Thank you. So, instead of interchanging rows etc. on F matrix, you can also do that interchanging on the unity matrix, get an elementary matrix and multiply F, the original matrix, by this elementary matrix. You will be getting the same end product. All right. Let us.
So why do you do this transformation?
Pardon? Elementary transformations.
Yeah, the second one.
We will see what it what use it has, because we have already used it earlier in the formation of the tree elements. It is not in the formation of the tree. For selecting the elements, we have gone through this operation. So, we shall be using this theory of elementary matrix transformation for the formation of the Q matrix. From A matrix, can you generate Q matrix? This is what actually we are aiming at. So, we will take it up later on. Right now, let me just demonstrate this, how simple multiplication by the elementary matrix will generate the new transformed matrix of F. Suppose F is given, I am taking just as an example a very simple matrix, -1, -1, 0, okay, 1, 0, 0, then 0, 1, -1. So, we want to interchange rows 2 and 3, row 2 and 3 interchanged. So what do you get? Minus 1, 0, 0, 1, sorry, 0, 1, minus 1, 1, 0, 0. Okay. What is an identity matrix? 1, 0, 0, 0, 1, 0, 0, 0, 1. And if I make row 2 and row 3 interchange, elementary matrix, I will call it epsilon matrix, 1, 0, 0, 0, 0, 1, 0, 1, 0. Now, if I, instead of doing this operation on F matrix, I am doing it on E matrix, identity matrix. All right. Now, what is E1 into F? What is E1 into F? 1, 0, 0, 0, 0, 1, and then 0, 1, 0 multiplied by minus 1, 0, 1, 0, 0, 0, 1, minus 1. Okay. What will be the end products? You are getting minus 1, 0, 0, 1, minus 1, 1, 0, 0. It is same as this one. That means the interchange operation which we are doing on F is as good as multiplying F by an elementary matrix.
With the same operation on the elementary matrix.
True. This is one elementary matrix. That means by, instead of doing it on the original matrix F, I will be multiplying by different elementary matrices. Different elementary matrices. I will get the same F.
So don't we think that like we are doing one extra operation here?
Apparently so. You will find.
On the surface it appears to be so.
Yes. So in this process, what we are trying to achieve, that Q matrix, what was Q matrix equal to?
This is equal to a QL or Q.
Q.
Unit matrix combined with the QL.
Finally, Q matrix was AT inverse A. Is it not? AT inverse A. So QF is basically U and AT inverse AL. All right. That was QL. So if by transformation of this AT A matrix, somehow if we generate a unity matrix here, from A if we go to Q, if I can make a unity matrix here, then this will automatically be generated. We will see that later on. So if you remember, from A matrix we started for making a tree, we are just getting the echelon form. If we try to make go a little further to get a unity matrix in that side, that means select a tree and then try to get a unity matrix there, then rest of it will be QL. You will get the transformed A will become Q. So this is what our aim will be. Before we go into that operation, I thought it would be better if we can work out one or two simple examples, some kind of a tutorial exercise on whatever we have done so far. Okay. There is a simple question. Can you draw the graph A is given? Can you draw the graph? I will read out the values. 1, 0, okay, 1, 0, 0, minus 1, 0. then 0 0 0 minus 1 1, then 0 0 0 0 0 minus 1 0 0, then 0 1 minus 1 0 0, then minus 1 1 0 0 0, then 0 0 0 0 4 zeros minus 1, then 0 0 1 minus 1 0, then minus 1 0 1 0 0. It is quite an involved network. So, there are 1 2 3 4 5. How many nodes are there? There is a reference node. Why? Because in column 3 you will find there is one missing, column 3, and column 5 6. So, if I call it 1 2 3 4 5 6 7 8, it is an 8 element vector. Node 1 2 3 4 5, then 6th one is the reference. So, 6th one will be this one plus 1 and this one plus 1, rest are all connected inside. So, node 1 it is okay, element 1 is between node 1 and node 4, 1 and 4, element 1. Element 2 is between 4 and 5, element 2. We will put the arrows later on. Node element number 3 is between 3 and 6, between some 6 and 3. Then element number 4 is between 2 and 3. Okay, let me put it here. Element number 4 is between 2 and 3. Element number 5 is between 1 and 2, between 1 and 2, element number 5. Element number 6 is between 5 and 6, this is 6. Element number 7 is between 3 and 4, between 3 and 4, that is element number 7. Element number 8 is between 1 and 3. Is that all right? So, this is the graph. You can always draw like this and then put the arrows depending on the plus 1 and minus 1 signs.
How do we decide that the reference is between the, if the sign is like plus 1 then?
See 1 1. So, both of them, there can be only two elements, one plus 1 and one minus 1. So, to find out where the ones are missing, there is only one element here, plus 1 is missing. So, that will be connected to the 6th node which is missing, reference.
But it could have been connected to other node also in the same column.
Possible. Then you have to select whether it is A or AA matrix. I asked you whether it is A matrix or AA matrix. Suppose it is given as some incidence matrix. Is it the complete incidence matrix or that reference matrix, normal incidence matrix that we deal with without the reference? Okay. So, since in these two columns we find these two elements are missing, so there is another row, another node, 6th node. So, we plot accordingly. Okay. So, this is the complete graph. Next question is find different trees using the matrix and then check the results on the figure. Find different trees. So, from this matrix you have to do that operation by that echelon forms. You have to find out the possible trees. There can be many trees and This is one example. Next, we take another example. There is an incidence matrix A, which is given here 1 0 0 0 minus 1, 1 2 3 4 5 elements. Next 1 0 minus 1 0 0, next 0 minus 1 0 0 1, then 0 0 1 0 0, okay, 1 2 3 4, then 0 0 0 minus 1 0, okay, then 0 0 0 minus 1 0 1 0, then 0 4 zeros and 1, okay, then 0 minus 1 1 2 3 4 5 6 7 8th row, 1 2 3 4 5 6 7 8th row, 0 minus 1 0 1 0, then 1 0 minus 1 0 0, then 0 0 0 0 1. Question is, without drawing the graph, indicate which branches are in parallel and which are in series. Do you get my point? There is a network. I am not drawing any particular graph for this. Two elements are in parallel. Which elements are in parallel? And which are in series? In series means what?
6, 8.
There is no other interconnection here. Okay? Suppose this is some node P, then there are two elements which are coming like this, which are in series means, what does it mean? At that node there will be a plus 1 and minus 1, and these elements are connected to some other nodes, then only in series. And okay, thank you. If these two nodes are in parallel, same starting and finishing nodes. So do you find any such? See, this and this, see, 1 2 3 4 5 6 7 8 9 and 10. So 6th and 8th,
Yeah, minus 1.
are they in parallel? And then 7 and 10,
17.
7 and 10 are in parallel,
Yes.
is it not? They are having the same 1 1,
Minus 1 is uniseparate.
minus 1 is in the reference.
Yeah, possible.
Okay, so 7 and 10 and 6 and 8, all right, they are in parallel. And what about series?
At the same node, there will be plus 1 and minus 1.
At the same node?
One will be plus and another will be minus. It's another column. Sir, 2 and 4
Node 2,
and 4.
node 2,
For node 3, element 2 and 4.
element 2 and 4, node 3, but what about element 9?
11.
Element 2, 4 and 9.
Yeah.
So there is not,
They will be going from the.
are they in series then?
Maybe parallel.
Are they in series then? Not in parallel, Suppose there is a branching like this,
Like this.
will you call it in series? So, is there any such element here? No. Any such element in this node? 1, 1, 1. No. Is there any such element here? No. Is there any such element here? No. Nor even here. So, that kind of a node is not present here. It is possible.
Because of 9. Otherwise it could have been present.
Then there will be only 1 plus 1 and 1 minus 1 in a particular node. Alright. More than 2 elements will violate that condition. Okay. We will stop here for today and we will continue with that echelon form and that elementary transform in the next class. Thank you very much. Good morning, friends. Today we shall be discussing about computer generation of topological matrices. Now, generation of the matrices BF and QF is quite a formidable task. We have seen how to generate A. Now, A, we started off with a 0 element matrix and then we filled it up with plus 1 or minus 1 depending on the interconnections between various elements. Now, for QF, it is, if you remember, it is AT inverse into A, AT inverse into A, and BF was unity matrix and AT inverse AL. Okay, sorry, BF transpose was minus of AT inverse AL and a unity matrix. All right. So, computation of this will require computation of AT inverse. Now, if you are having say 50 or 60 node system, 50 or 60 node system, then it is not advisable to go for the inversion of such a matrix, because AT will have the dimension 50 by 50 or 60 by 60. All right. So, if AT